Okay.
Okay, so what I'd like to do today is to go over more of these Lewis structures, because that's going to be the main focus of this chapter, is drawing Lewis structures and analyzing Lewis structures, that sort of thing.
Good morning, Professor.
Good morning. So let's take a look. Let's take a look at some Lewis structures here. I'm going to go straight to some of the Alex problems. And the one that we looked at yesterday was figuring out the compound. Let's take a look here. Okay, so this particular problem is called deciding whether a Lewis structure satisfies the octet rule. Okay. So what they do is they show you a Lewis structure. So remember, the pair of dots, that's called a lone pair or a non-bonding pair, and that's 2 electrons. And then we have, let me move this out of the way a little bit just in case someone comes in. There we go. We'll move this over here. Okay. So we can also represent a bond with one of these lines. It's called line notation. And the bond is, again, 2 electrons. So a bond is 2 electrons. A lone pair or non-bonding pair is also 2 electrons. And what we said was that for many elements, many of the nonmetals, there appears to be a tendency to have structures in which there are 8 valence electrons around the atom. And that's called the octet rule, right? So octet is 8. And you're going to see octet when you do things like nitrogen and carbon and oxygen and fluorine and chlorine and bromine and iodine, the nonmetals, right? And then we said there was something called the Duet Rule, but that was only for hydrogen. Okay. And then later on, we'll look at some structures where actually it turns out, arguably, we can observe what appear to be violations of this octet rule. We'll see. So here's how you go about it. You do each atom separately. Okay, so I'm going to start with the chlorine over here. And I'm just going to count up the number of electrons around that chlorine. So you have a bond. So you count that bond as 2 electrons. So that counts as 2. You count each lone pair as 2. So you have 2, 4, 6, 8. So I'm going, I'm going clockwise. You don't have to go clockwise. I'm just sort of going in this direction. But I'm starting with the bond, right? So there's 2 with the bond and then 2 with each lone pair. So that chlorine has 8 electrons, 8 valence electrons, right? And we said valence electrons was important because if you can get up to 8 electrons, that gives you the same number of electrons as a noble gas has in its valence shell. Okay. So now let's do the oxygen over here, up at the top. Same idea. You start with the bond, and you can move either clockwise or counterclockwise. You just count all the electrons around it. So the bond has 2. Each lone pair has 2, so that's a total of 8. So octet rule. Looks good so far. Let's try the carbon in the center. So I'm going to start with the lone pair and count around the carbon. Okay, you have the lone pair, then you have 3 bonds. And remember, each bond is 2 electrons. So that's 2, 4, 6, 8. So it looks like the carbon also has 8. So far, so good, octet rule. And then the chlorine, I guess I'll start here at the bond. We'll just go around until we run out of valence electrons. And again, 1 bond, 3 lone pairs. That's going to give you a total of 8 electrons. So notice there's different ways to get 8, right? So the carbon has 3 bonds and 1 lone pair. That gives it 8. all the surrounding atoms, the chlorines and the oxygen, they have 3 lone pairs in 1 bond, right? So that's a different way to get 8 electrons. So we would have to say 1, it appears as though it's following the octet rule. So that looks good. The next thing we're going to do is we're going to analyze whether it has the correct number of valence electrons. So it appears to have 8 electrons around each atom. So that looks good, right? The problem is, so there's a question mark. The problem is that you can draw 8 electrons around each atom, but that may not be what actually happens because you may be creating the wrong number of electrons. So we have to make sure, we have to do some counting here to see whether we have the correct number of valence electrons. So let's count up how many we have. Be careful because the bond is 2, but it's shared between each atom, right? So you don't want to count it twice in terms of counting the number of valence electrons. So I'm going to start right here. I'll start right here. I'll write a little asterisk right there just to say we're starting here. And I'm just going to kind of go around. So there's 2, 4, 6, 8. So there's 8 there. 10, 12, 14, 16, 18, 20, 22, 24, 26, it looks like, right? I don't want to count this again. So that's 26. So I'm going to check that. Let's make sure. 8 around here, 8 around here. So that's 16, 24, 26. It looks like there's 26 valence electrons. And now here's how you check to see if that's the correct number. In order for a Lewis structure to be correct, it doesn't just have to have the octet rule. It also has to have the correct number of valence electrons. So let's check this out. We've got a carbon. Carbon is in group 4A, so it has 4 valence electrons. Chlorine is in group 7A, so it has 7 valence electrons. But there's 2 chlorines, so let's do another chlorine. So it also has 7. And then oxygen is in group 6A, so it has 6 valence electrons. So if that adds up to 26, we're in good shape. We got a pretty good Lewis structure right here, okay? So let's see. 4 plus 7 is 11, plus 7 is 18, plus 6 is 24. We have the wrong number of electrons. So see how it didn't equal what we have over here? What that tells us is we made a mistake in this Lewis structure. We got rid of a couple of, I'm sorry, we added a couple of electrons. We have 26 in there, but the actual structure only has 24, okay? So that structure is no good. So what we would say is that, yeah, it obeys the octet rule. The symbols are okay, but it just doesn't have the correct number of valence electrons. We got to have the right number of valence electrons. So let's take a look at another example. Okay, I'm going to do this one here. Classic molecule here. This is dinitrogen. It's N2. It's in our atmosphere. Okay, so let's take a look at this one. Okay, let's do the octet rule first. So I'm going to start with the nitrogen on the left. Let's start right here. We got 2 here, and then we got 6 electrons there, right? A triple bond. That's called a triple bond. Isn't that cool? That means there's 6 electrons in that bond. And we're going to talk a little bit more when we get into chapter 9 about the meaning of that. It's a fascinating study to look at what that means. But there are 3 pairs, 6 electrons holding those 2 atoms together. So you got 2 over here, and then you got 6 there. So that's 8. You got 8 electrons here. That's good. Do the same thing for the other nitrogen. We'll start over here and go around. Again, you're going to count that triple bond again because those electrons are being shared by both atoms. So 2 plus another 6, again, we got 8. So octet rule is good. Just like in the previous example, we got a good octet rule. But we want to know if we have the correct number of valence electrons. Okay, well, let's count them up. It looks like we've got 2 here and we've got another 2 over there, those lone pairs. So that's 4. And then we've got 6 electrons in between. So that's 10. So it looks like we got 10 valence electrons. Now let's count how many we should have. It's N2. So nitrogen is in group 5A. So it has 5 electrons. And there's 2 of them. So there's a total of 10 electrons. So we're good, right? We got the correct number of electrons. As long as the number of electrons in the Lewis structure matches the number that we should have from the periodic table. And we have octet rule, at least from a starting perspective, that looks like a good Lewis structure. We'll get look at more nuanced type of issues that come up later and some exceptions. But for the most part, that's pretty much how it works. We've got 8 electrons around each of those atoms, and we have the correct number of electrons. So notice there aren't 16 electrons, right? We don't have 16 valence electrons. We don't have to have 8 only for each atom, right? We don't need 8 plus 8 to get 16. We just need to have a total such that each one either has 8 on its own or is sharing up to 8, right? Sharing so that the total number is 8. That's the octet rule. Let's look at one more. This one's a little bit more difficult because it's an ion. So this one, I'm going to put my bracket around it. And then I'm going to put a negative there for the charge. And we have 3 lone pairs over here on the left. Now, if you recall, yesterday what we said was that if you have an ion, if it's negative, you add an electron. You add an additional valence electron. If it's -2, you add 2 valence electrons, so forth. If it's positive, you remove, right? It's positive means it's lost electrons, so you remove electrons. So this one, we're going to add an additional electron. So before I do the octet, let's count up our valence electrons first, okay? So I'm going to count, I'll start over here on the left. We'll start over here and move this way. So we've got 3 lone pairs around the nitrogen and then a bond, so that's 8. Then we got 2 for the lone pair, and then another 4 for the bond, the double bond, right? There's 2 bonds there, so that's 4. And then we got another lone pair here, so that's 2. So that's a total of 10, 14, 16 electrons. So that's what we've drawn. We've drawn enough dots and bonds to give us 16 electrons. Let's check it. 2, 4, 6, 8, 10, 12, 14, 16. Now let's count up the number that it should have based on the elements that are in the substance, in the ion, and the fact that it is an ion, right? So nitrogen, again, is in group 5A. But there's 3 nitrogens, so 3 times 5, right? 5 plus 5 plus 5. But then don't forget this extra charge here. So plus 1. So that's 16. So it looks good. We got the correct number of electrons. That matches. So the number of dots and bonds is equaling the number that we would get for each atom based on its position in the periodic table and the fact that it's negatively charged, that additional extra electron. Okay. Now let's do the octet. The atom on the left is in good shape. You can see that it's in good shape, right? It has 3 lone pairs, so that's 6, plus a bond, that's 8. So this guy's in good shape, it's got 8. But look at the next atom. The next atom, I guess I'll start over here with the lone pair. We have a lone pair, a double bond, and a single bond. So that's, again, another 8. That looks good. Now let's do the nitrogen on the right side. The nitrogen has 1 lone pair and a double bond. Now that's only 6. Okay, so there's your problem right there. You have the correct number of electrons, but they're not distributed properly so that each atom has 8. This one only has 6. So I'm going to show you what you can do to fix it. Very simple problem. I mean, very simple issue. I'm going to fix it for you. Because we have the right number of electrons. The problem is this one over here, that one on the right only has 6. So we can't just add 2 more electrons, because then you would have 18 electrons, and N3 minus doesn't have 18 electrons. It only has the 16 to work with. So you have to work with the ones you have. So here's what I'm going to do. I'm going to redraw it over here at the top, just so you can see it. Okay. If you look, we have a lone pair over here. I'm going to circle the lone pair. And what I'm going to do is I'm going to draw an arrow, and I'm going to push that pair of electrons to form a third bond between those 2 atoms. And when I do that, I'm going to indicate that I'm pushing electrons. There's 2 things you do to indicate that. One is you draw a little arrow here pointing where the lone pair is going to go. And then you use a double-headed arrow, right, and a head on both sides to indicate that you have a new Lewis structure. So now, instead of having a lone pair on that middle, on that central nitrogen, we're now going to have 3 bonds, right? So that lone pair has created a bond. Okay, now I'm sorry, I forgot to put the brackets. There's a lot of notation here, brackets, arrows, different context of arrows, okay? Now, take a look at this one over here on the right. Now...
I'm sorry, Professor. May I ask you a question?
Sure.
Is this bond always comes to the front, not to the back, right? Like, why you didn't put it by the first end?
Oh, because if I put it on the first end, then that nitrogen on the left would have had 10 electrons. We're trying to get them up to 8.
Oh, okay.
So take a look. So right now, each of these have 8, and this one has 6, right? That's what we did down here. Now take a look. The one on the left still has 8 because we haven't done anything to it. So it's still going to have 8. But the one in the center still has 8, even though we took a lone pair away. And that might seem weird. Like, wait a minute, I took a lone pair away, so why doesn't it just now have 6? The reason is we didn't take it away. We pushed it between that atom and the next atom. So now it's a triple bond. So that's 6, and there's still the 2 over there. So this atom still has 8. Okay. But what we've done is we've fixed the problem on the right side. This nitrogen, which had a double bond and a lone pair, only had 6. It now has a triple bond. That's 6 right there, plus a lone pair. It now has 8. Okay, so that is called electron pushing. You can Google that, electron pushing. And we're using what's called arrow notation. So this is where you use a little curved arrow to indicate that a lone pair is now becoming a bond. And so I can say right now that the evidence suggests that something like this does happen in nitrogen, in nitride. I'm sorry, this is called azide. This is called the azide ion. Okay. And but what we've done is we've fixed it. So now each atom has 8 valence electrons, either shared or as lone pairs. We still have the correct number of electrons. I haven't added or subtracted any electrons. I've just changed them from being a lone pair into being a bond. So in fact, we can go back. Do this. Oh, no, we can't go back to that one because that one has the wrong number of electrons. So let's take a look at another example. That one had the wrong number. So you can only do this if you have the correct number of electrons. You can't have the wrong number of electrons and expect that to work. Okay. So let's take a look. Let me see. 4, 10, 2, 4. Okay, so that one's the wrong number of electrons. Yeah, let's try this one. So I'm going to do HCN. This is another one. Okay, so let's do the first step. I recommend, instead of doing the octet first, check to see that it has the correct number of electrons and then do the octet. Okay, So let's count up the number of electrons here. We have 2 on the left with this bond. We have 2 with the lone pair, so that's 4. We have a double bond, so that's 8. And then we have another pair, so that's 10. So we got 10 valence electrons. Okay. Now we're going to compare that to what it should be based on the position in the periodic table. Now it's not an ion. There's no negative or positive. So that means we just count up the number of atoms from each element. So hydrogen is in group 1A. So it has 1. Carbon is in 4A. So it has 4. Nitrogen is in 5A. So it has 5. So that's 10. Good. We're set. We have the correct number of electrons. Now we can check the octet rule, but be careful because hydrogen, again, is the duet rule. So we just want to make sure that hydrogen has 2. And it does, right? The hydrogen doesn't have any lone pairs. It has 1 bond. So it's got 2. So that's good, duet rule. Now let's do the carbon. Carbon has 1, 2, 3 bonds and a lone pair. That's 8 electrons right there. 2, 4, 6, 8. And the nitrogen, now this is a problem, right? If you look at this nitrogen, it has 2 bonds, so that's 4, and 1 lone pair, so that's 6, so it doesn't have 8. Okay, so there's your problem. So very similar to the one we just did with the N3 minus. That one, the nitrogen on the right didn't have enough electrons, same thing here. So here's what we would say about this. We've got the correct number of electrons, we just haven't drawn the proper Lewis structure. So let's see if we can fix it. Okay, so remember our tool is this electron pushing, right? You take a pair of electrons that's a lone pair that's on one atom. Let's draw it a little bit differently. And you push it so that it becomes a bond. And then you use this double-headed arrow to indicate that this is now an extra bond between those 2 atoms. Okay, that's called electron pushing. In organic chemistry, sometimes what they do is they just push 1 electron. So you might have this kind of structure. And if they're going to push 1 electron, then you just use a half-headed arrow, right? Because you're only pushing 1, so it's not a double-headed arrow, it's just 1. But we're not going to do that in this course. We're just going to use this right here. Okay, the reason you do that is because the atom that you're pushing the electrons toward doesn't have enough. If it doesn't have enough electrons, a tool you can use is to push a pair, or 2 pairs even, of lone pairs, these non-bonding pairs, so that they're shared between the 2 atoms. So take a look, the nitrogen has 6, so what do? We push this pair of electrons so that that pair of electrons is now going to form a new bond. And then use this double-headed arrow to indicate that it's a new Lewis structure. So it's no longer a lone pair, it's now a bond. And even though, again, you might think the carbon has now lost 2 electrons, it has not lost 2 electrons. It has just shuffled them around to become a bond to the next atom. So now this nitrogen is good to go. It has 3 bonds, which is 6, plus a lone pair, which is 8. The carbon now has 4 bonds, which is 8. And the hydrogen has 1 bond, which is 2. So that one's in good shape. Okay, let's take a look at, let's see, 2 electrons. That one might, well, that one's, they've each got 8. Okay, let's take a look at one that's got to be wrong. I'll show you this one here. This is an easy one. Okay, so again, you're doing 2 tests, right? One is, does it have the correct number of electrons? And then 2, are you following the octet rule and the duet rule for hydrogen? Okay, so I can say right here that if you look at this, you can immediately see that this is a bad structure. This is not a proper Lewis structure, and here's why. Take a look at this hydrogen here. It has a bond here and a bond there. So that means it has 4 electrons, right? That's breaking the duet rule. Remember, hydrogen is the duet rule. So that right there tells you this is not a good Lewis structure because the hydrogen does not have 8. Okay. The other 2 hydrogens do have, I'm sorry, the hydrogen does not have 2. The other 2 hydrogens are okay, right? That one's got 2. It's got 1 bond, so that's 2. This one's okay. It's got 2. It's got 1 bond. The oxygen's no good either, though, right? If you take a look at the oxygen's a problem because it's got a bond, and a lone pair. That's only 6. It's only got 6 electrons, so it doesn't have 8. So oxygen, we want that to be the octet, which is 8. So the problem here was this hydrogen had 4, this oxygen has 6. That is not a good Lewis structure. Okay. Now let's also check to see if it has the correct number of electrons. So each bond is 2. So there's 2, 4, 6, and then there's your lone pair. So that's 8. So it's got 8 electrons. And then let's count up based on the position in the periodic table. You got 3 hydrogens, and then you got an oxygen. Okay, and then it is charged. Let's not forget that. It has a charge of +1. We'll deal with that one separately. So 1A is 1 electron group, 6A is 6, so that's 9, but it's a plus, right? So that means you subtract 1, so it has 8 electrons. That's good. It actually has the correct number of electrons. 8 electrons is the correct number of electrons. The problem is this Lewis structure doesn't work in terms of the octet rule. So you might say, okay, well, maybe we could push electrons around. Maybe we could push some around and make it work out, right? We got the correct number of electrons. So maybe what we could do is we could push, I don't know, we could push this pair of electrons over there. Can you do that? And it turns out the problem with that is that if you push that pair of electrons, this hydrogen on the left is no longer bonded. It would be all by itself, and you'd have this. You wouldn't have a molecule anymore. You wouldn't have this polyatomic ion. It's no good, right? Because we have to have at least 1 bond between each atom in our Lewis structure. So that's no good either. So you can't even use electron pushing to fix this problem. So then you say, okay, well, what's the problem? If you look at the chemical formula, 3 hydrogens, 1 oxygen, and it's positively charged. That's actually what we're trying to draw the Lewis structure for here, H3O+. And we know that exists. This is called the hydronium ion. We talked about that in chapter 4. It is, in fact, something that exists. So we have the correct number of electrons, but we don't seem to be able to fix the Lewis structure without breaking the molecule or breaking the ion. So how do we deal with that? In this particular case, the problem was they didn't arrange the atoms correctly. They put a hydrogen bonded to a hydrogen. And the only time hydrogen bonds to hydrogen is in the case of H2. That's the only time it really does it. So you can't have a hydrogen bonded to hydrogen. So here's what ends up happening. If we had put the oxygen at the center and then surrounded it with hydrogens, so there's your H3O+, that would have given us the correct Lewis structure. So the real issue is not that they didn't put the electrons correctly or that they had the wrong number of electrons. They just didn't arrange the atoms correctly. So that's an important part of drawing Lewis structures as well. We'll look at that, which is that you not only do you have to get the electrons right, you have to position the atoms correctly. So in the case of the hydronium ion, the oxygen is at the center and the hydrogen atoms are bonded to it. Whereas over here, they just gave us a structure where it appears as though the hydrogen is at the center. And that's not what really happens. Okay. All right. Let's see. Okay, we did that one yesterday. Did that yesterday. Okay. Okay, do a new slide here. Okay, so let's get back into our Lewis structures here. So this is going to be counting. So this is section 8.5, Lewis structures. Valence electrons. In a molecule or polyatomic ion. Okay, so how many valence electrons? Okay. All right, so how many valence electrons in CO3 -2? Okay, so let's go through it. So what you do is you look up where the elements are. So carbon is in group 4A, so it has 4. Oxygen is in group 6A, so it has 6. But there's 3 oxygens. So I'm going to multiply it by 3. So this is the number of oxygen atoms. So you get 18, right? There's only 1 carbon, but there's 3 oxygens. And then you have this negative charge, right? So the charge. So you have 2 electrons. Every time you have a negative charge, that's an extra electron. So our total then would be 4 plus 18 plus 2, which is 24. So this question really only asks you for the number of electrons, the number of valence electrons. So our answer would be 24. When you do these problems, you're going to see some numbers that come up pretty commonly. 8 is going to come up, 16 is going to come up, 24 is going to come up, and 32. Multiples of 8. And again, there's that issue of the octet rule. You know, it's just very common for these types of things to happen. So if you've got, you know, 4 atoms, you typically, so this has 4 atoms, 1 carbon and 3 oxygens, you might find 24 is pretty common. If you have 5 atoms, you'll find that 32 electrons comes up. If you have 3 atoms, 16 will come up. And if you have 2 atoms, 8 will come up quite often, okay? So there's 24. But now I want to go to the next level. I want to show you how to draw the Lewis structure. So here's what you do. You look at your chemical formula. And notice how there's only 1 carbon, but there's 3 oxygens. In general, molecules are formed with 1 atom at the center and the other ones around it, surrounding the one in the center. So you're often going to see stuff like this. See how you have 1 atom in the center and then 2 surrounding atoms branched off like a tree. Same thing if you have 3. Same thing if you have 4. This is just a very common way that molecules form, those particular structures. So if we look at carbonate, CO3 -2, the one that's only 1 atom, we're going to put that at the center. So the carbon will be at the center, and then it's going to have 3 oxygens around it. Okay. Oops. So I'm going to put this carbon at the center, and then I'm just going to put oxygens attached to it, like so. Okay. And it doesn't matter whether you put that oxygen on the top or you put it on the bottom. You could also do it like this. Well, I could do it like this. That's perfectly fine. There's no difference there. Or you could do like that. That's okay too. Doesn't matter where you actually draw them. Just, again, think of it kind of like a square, like when we were talking about Lewis dot symbols, Lewis dot diagrams. So that's the first step in drawing a Lewis structure, is to get that sort of arrangement of atoms. Remember, that was a problem with that H3O plus. They had the 2 hydrogens. So if we'd used this logic, the oxygen goes in the center and then the 3 hydrogens go around, that would have gotten us out of that problem. We would have gotten that Lewis structure okay. Okay. So typically this one in the center is called a central atom. And then these ones on the outside are called surrounding. Okay, central surrounding. And it doesn't work 100% of the time, but it works most of the time. It's pretty good. So now, how many electrons did we say we had? We said we had 24. So here's what I'm going to do. We already counted up the number of valence electrons. So step 1, get the arrangement of atoms correct. Step 2, get the number of electrons. So we have that 24 electrons. Okay. Now I'm going to distribute the electrons. And here's what I'm going to do. We already have distributed 6. So we're kind of ahead of the game, right? There's 6 right there. Each bond is 2, so there's 6. So I'm going to subtract those 6 electrons that are already used. And that gives us 18 electrons. So now we only have 18 to distribute. Okay. And what I'm going to do is I'm going to write them as pairs on the surrounding atoms. Look what I just did. I put 3 lone pairs on each atom. That's 6 electrons on each of those surrounding atoms. 3 times 6 is 18. So I've used them all. So now we're at 0. What that means is we have all 24 electrons distributed. Now remember, that 24 was 24 because we had the extra 2 there. So make sure you put your charge and the bracket notation here like that. Okay. Now we ask the question, is this done? Have we done enough of these to make it a reasonable Lewis structure? In the previous problems, we counted the number of valence electrons. So we've done that. That's good, 24. And then we checked the octet. So let's take a look. The oxygen on the left, it has 8. See that you can see that it has 8, right? In fact, all of the oxygens have 8. They're all good, right? They each have 3 lone pairs in a bond. That's 8. But the carbon only has 6. So by putting 6 electrons around each of the oxygens in the form of lone pairs, that's where these 18 electrons came from, right? This 18 that I used right there are those 3 lone pairs on each of those atoms. The carbon only has 6, so that's a problem. So what did we do to solve that problem last time? We took a lone pair and we pushed it to form a new bond between the atoms. And that lone pair can now be counted by both atoms because it's now a bond. And then we use the double-headed arrow to indicate that this was a new Lewis structure. So now we have a double bond, and then a single, and then a single. And then now you've only got 2 lone pairs, whereas with the other atoms, you've got 3. Okay. We've now got an octet around the carbon, but we also have an octet around each oxygen, so we're done. So carbon, oxygen, octet, 24 electrons, that's the correct number. Everything is correct in this Lewis structure. Now I could have picked this lone pair up here instead, But that's okay. That's going to give us the same thing. It's going to give us a double bond. It's just that you would have the lone pair down here at the bottom, right? You would have the lone pair down here at the bottom instead of at the top, right? So that's perfectly fine. Or I could have picked a different oxygen, right? I could have picked the oxygen on the right or the one on the top and done it over there. There's no reason that I picked this, that I have to pick this one up here, right? Okay, so I could have picked this one over here. And what would that have done? That would have given me a double bond over here. So it doesn't matter which oxygen you pick it from, and it doesn't matter which lone pair you pick. The point is we got to get that carbon up to 8. So we got to pick a lone pair somewhere around it from one of the surrounding atoms and get it over there, okay? Let's take a look at another example. Okay, so for this one, again, we're going to do the same thing. We're going to count the valence electrons. And then we're going to draw Lewis structure. Okay, so you look at the formula. You got one phosphorus, so there's phosphorus. Actually, let me do this up here a little higher up. Phosphorus is in group 5A, so it has 5 valence electrons. Bromine is in group 7A, so it has 7. But remember, there's 3 of them, so 7 times 3 is 21. There is no charge here. This is not a polyatomic ion. It's just a molecule. It's phosphorus tribromide, PBr3. So that means our total number of electrons is 5 plus 21. Now that's kind of interesting. It's 26, right? It's not 24 or 18 like I said you would often see, or I'm sorry, 16. So 8, 16, 24, 32. Sometimes you get 30, 26 as well. So how do we deal with this? We got the number of valence electrons. So same thing. There's only one phosphorus, so you put it at the center. And then there's 3 bromines, so you draw them as surrounding atoms. This time I'll put one of the bromines on the bottom. Doesn't matter where you distribute them. But again, think of it sort of like a square, right? So you got your central atom, and then think of a square. So one's coming up like this. And if you had 4 atoms, you would do it like that. If you have 5 atoms, then typically what people will do is they'll do it sort of like a pentagon like that. And then if you got 6, which does happen, then you kind of do it like that. Okay. All right. So now we've already used 6 electrons. There's 2, 4, 6. So I'm going to subtract those 6, and you got 20. Then I'm going to distribute them around the surrounding atoms first. So surrounding atoms, 3 lone pairs. And the reason I'm doing 3 lone pairs is because they've already got a bond. So they already have 2. We don't want to go beyond 8. So 3 lone pairs gives them 8. So 3 lone pairs. So that's 6, 12, 18. But I still have 2 more because I had 20, right? 18. You still have 2 left. Where do they go? Now you put them on the central atom. If you have any more after you get the surrounding atoms up to 8, put that extra pair or 2 pair, if you have 2, put them on the central atom. And here's a really nice thing about this structure. Every atom has 8, so there's no electron pushing required. So the bromine has a bond and 3 lone pairs, so that's 8. This bromine has a bond and 3 lone pairs, so that's 8. This bromine has a bond and 3 lone pairs, so that's 8. The phosphorus has 3 bonds, so that's 6, but it also has a lone pair, so that's 8. So we're set for Octet rule. Okay, so you only need to do the electron pushing when the central atom doesn't have enough, doesn't have 8, only has 6. If it has 8 already, you're set to go. Okay. And again, the first bond, that's 2. So the reason we subtracted 6 is because we have to have at least one bond. So we're going to put one bond in there when we are doing the arrangement of the atoms. Let's try one more. That's the same one. I don't know why I did that. Okay, this one's a little trickier. First step's easy though. We're just going to count the valence electrons. That's easy. Okay. So we have 3 elements. We have carbon, we have hydrogen, we have oxygen. So let's do hydrogen. Hydrogen has 1 valence electron, but how many of them are in there? There's 6 hydrogens, right? 3 plus 2 plus 1. So you got 6 valence electrons there. You also have carbon. Carbon is in group 4, so that's 4. But there's 2 carbons. So that's 8. And then there's 1 oxygen. Only 1. So now no charges, it's not plus minus, so we can add these up. So our valence electrons is 6 plus 8 plus 6. So is that 20? 20 electrons, okay? So that's really the first step, is counting the number of valence electrons. So each atom, just count them up. Now let's try to do the Lewis structure. This is kind of a fun one. This is called ethyl alcohol. Here's how you deal with multiple carbons. Okay. See how you have 2 carbons? Here's what you do. You identify the carbons and any element that's not hydrogen. Ignore the hydrogens at first. And then you connect the carbon atoms with a single bond. Just connect the carbon atoms. So you got 2 carbons, so you connect them. Okay? Then you look for the elements that are not carbon and the elements that are not hydrogen. We're going to do hydrogen last. So see how there's 1 oxygen? You assume that oxygen is connected to the carbon that's closest to it right there. Okay? So that carbon is now connected to this oxygen on the right. Okay? If it were nitrogen, same thing. If it were sulfur, same thing. So do the carbons, then do any elements that are not hydrogen, connect them to the closest carbon. And now you do the hydrogens. The hydrogens are typically drawn right after the element that they're bonded to. So you see how it's CH3? Those hydrogens are bonded to that first carbon, CH3. Okay, so that's drawn as CH3. And then the next 2 hydrogens are bonded to the carbon that it's closest to, the one that comes right after. Typically, you write the hydrogen after the carbon. So CH2. And then if there's a hydrogen after the oxygen, you draw that to the oxygen. Okay. So there, it's kind of cool. It works most of the time. I mean, there's some weird exceptions to that, but it works most of the time for the simple ones. So CH3, CH2OH is 3 hydrogens on the first carbon. That carbon is attached to the second carbon. That carbon is attached to the oxygen. And then it's 3, 2, 1 in terms of the number of hydrogens. Okay. So there's your skeleton. There's the structure. Now, the next step is to count the electrons. Now, it turns out we've already done most of the electrons. We're in pretty good shape. These are easy to draw Lewis structures for because each bond is 2 electrons, right? So if you count up the number of bonds, I'm going to start over here. I'll go this direction. 1, 2, 3, 4, 5, 6, 7, 8. You got 8 bonds. Those are from the bonds. So you've already used 16 electrons. So 20 Remember what we did before? We subtract the number of bonds. So now you only have 4 electrons remaining. So it's the number of electrons you started off with, 20, minus the ones we've already used just by drawing this arrangement of atoms. Okay, we've only got 4 to go. So now, again, put them on the surrounding atom. But remember, hydrogen can only handle 2, so you're not going to put them on hydrogen. The only atom that's left is either carbon or oxygen, but the carbons already have 8. So you're not going to put them on the carbons. You got to put them on the oxygen. So 4 electrons, there's 2. There's another 2, there's 4, and your Lewis structure is done. These are really fun to draw. The organic molecules, these hydrocarbons, are really cool because what happens is, you use so many of the electrons when you draw the CHs and the CC bonds that you only have a few to remain to put over there. And you end up with a pretty good structure. Okay, so that would be a Lewis structure for this molecule, which is called ethanol or ethyl alcohol. Could do that one, but let's see. Yeah, let's try one more. This is called the acetate ion. Okay, so first step, let's count the number of valence electrons. Okay, so we have carbon, group 4A, 4 electrons, but there's 2 of them, right? There's 2 carbons in there, so times 2 is 8. You've got hydrogen, which is group 1A, but you've got 3 hydrogens, so that's 3. You got oxygen, so that's 6, but there's 2 of them. And then you have the negative. Don't forget the negative. So you got 1 there. So you got 8, 3, 12, and 1. So what is that? 8 plus 12 is 20, so it's 24. Okay, so number of valence electrons in that would be 24. The next step is to draw the arrangement. Okay, so here's again, same idea. Connect the carbons together, right? Ignore the hydrogens you're going to do at the end. So you connect the carbons. And then I said connect the next atom, which is not a hydrogen. So there's there. So now here's where you really got to be careful. If you have COO minus, that arrangement is like this. Okay, I'll put the negative here. Okay. So COO minus is generally written as C double bond O bond O. So I'm going to do it like this. Okay. Now notice by putting the double bond O, that's 4 electrons. So you got to take that into account that I'm drawing 4. Okay. Now you go back and you do your hydrogens. The hydrogens are drawn after the carbon that they're attached to. So that would be this one. Okay. Now I'm going to make sure that I don't forget to put my bracket and the negative there. But now we got to distribute the electrons. Okay. We had 24. How many have we used so far? We start over here. I'm going to count in this direction. 2, 4, 6, 8, 10, 12, 14. Is that right? Yeah, 14. So we got 10 to go. Surprisingly large number, right? But remember, if you take a look at the hydrogens, they only need 2, so they're done. The carbons only need 8, so they're both done. Both carbons have 8, right? The carbon on the right has 4 bonds, so that's 8. So the only thing left is the oxygens. And again, the oxygens are surrounding atoms. So what you do is get them up to 8. So 2, 4. So that one's now up to 8. Don't forget the double bond. That's 4 right there. 6, 8, 10. So I've used all 10. That looks pretty good. Now this oxygen has 8. In fact, it worked out perfectly. The oxygen on the right has 8. The oxygen on the top has 8. The oxygen on the top has 2 lone pairs. The oxygen on the right has 3 lone pairs. 2 lone pairs and 3. That's 10 electrons. So you're set. So when you see COO minus or COOH, the arrangement that you want to do is this. Okay. Those are called organic acids. The organic acid with the hydrogen or without it is a very important type of acid, and they are typically drawn in this form, CH3COO minus or CH3COOH. Let me show you one more of those. Okay, this is called glycine, and it is an organic acid. You can see it's an organic acid because it has that COO right there, right? So this would actually, the formula might be drawn this way. NH2, CH2, CO2 minus. I'm sorry, COO minus. Okay, so there's your chemical formula. The Lewis structure looks like this. 2 lone pairs, just like we did over here. 3 lone pairs, just like we did over here. And then it's negatively charged. So glycine is an organic acid, right? And when you have the COO minus, that tells you it's an organic acid. So one of the oxygens is going to have a double bond to the carbon, and the other one is just going to have a single bond, right? Just a single bond to that one over there. Okay. Okay, let's see. I think that's pretty much it for those. We'll come back and draw more of those structures next week. So what I'm going to do next week is I'm going to kind of go back and start talking about electronegativity, which is section 8.4. We'll do that on Tuesday. And actually, when is this due? Oh, this is not due till June 6th. Okay, we're good. And then we'll come back and do more Lewis structures, and we'll just keep working through it. We're still kind of, I wouldn't say that we're even halfway through this chapter. We're really sort of still, kind of learning how to do these Lewis structures, but we'll get more practice with it. The whole chapter is really about drawing Lewis structures, so we'll get a lot of practice doing this. Okay. So have a great day. Reach out to me if you have any questions. Have a great weekend. And I believe it's the end of Ramadan. So happy end of Ramadan as well. And take care, everybody. Bye-bye.
Thank you,
Thank you.
Professor.